Helicopters. The helicopter belongs to the flight machine category with the highest operational efficiency because it does not need takeoff and landing grounds and it can be used to its utmost capabilities. For short and medium ranges, the flight efficiency of helicopter is comparable with those of the airplanes. We are going to discuss about few of the math components involved in the making of helicopters and flying of helicopters. First one is blade element momentum theory. It is a simplified model used to calculate the lift and the drag forces which acts on the rotor blade of an helicopter. The basic idea is to divide the blade into small sections and then to integrate the forces acting on it. This will provide us the total lift and drag on the blade, and then it can be calculated by summing up the contributions. A few assumptions which we take while calculating blade elemental momentum theory is the air flowing over the blade is inviscid. That means there is no resistance of the air, and the blade is rigid and it does not deform. The air flowing over the blade is uniform in both speed and direction. The blade is modeled as a collection of independent blade elements. So the equation goes as L is equal to rho AB into A. L is the lift force, rho is the air density, A is the area of the blade, and B is the free stream velocity. And A stands for axial induction factor. The drag force can be calculated by using a similar equation, which is D. D stands for drag force, rho into AB multiplied by C and D. D is the drag force, CD is the drag coefficient, which depends on the airfoil properties of the angle of attack.
The next component we're going to talk about is Euler-Lagrange's equations. Euler-Lagrange's equations are used to describe the motion of a rigid body in three-dimensional space. In helicopter engineering, these equations are used to model the motion of the helicopter and its components. The equations are based on the principle of least action, which states that the motion of a system is determined by the path that minimizes the action of integral. The Euler-Lagrange's equation can be written as d by dt of dou L by dou Q minus dou L by dou Q is equal to Q, capital Q. The Q is a vector of generalized coordinates that describes the position and orientation of a rigid body. L is Lagrangian operator which describes the kinetic and the potential energy of the system. Capital Q is generalized force vector and the dot notion represents the time derivative.
Moving on to Laplace transform. Laplace transform is a mathematical technique used to simplify the analysis of complex dynamic systems. In helicopters engineering, it is used to analyze the response of helicopters to various inputs such as control inputs and external disturbance. The Laplace transform of a function f of t is defined as f of s integral of 0 to infinity f of t into e power minus st into its derivative, where s is a complex variable and the integral is taken over the range of 0 to infinity. The Laplace transform converts a function from the time domain to frequency domain, which simplifies the analysis of dynamic systems.
Control theory. Control theory is used to design and analyze the performance of helicopter control systems. Mathematical techniques such as feedback control and optimal control are used to design control systems that stabilize the helicopter and achieve desired performance. The basic idea behind feedback control is to measure the output of the system and use this information to adjust the input to achieve a desired response. The equations used in control theory depend on the specific control system being designed. For example, a simple proportional integral derivative controller can be described by the equation u of t kp e of t plus ki integral 0 to t e tau v tau plus k. Thank you.
Recording.